welcome to the deep dive. Today we're tackling a really core challenge in distributed systems, concurrent writes.
Yeah, this is super important stuff, especially, if you're prepping for those senior software engineer interviews.
Exactly, the system design ones. So we've looked at some material discussing how concurrent writes are handled, things like version concurrency control.
Causal dependencies, too, and those tricky issues you get with multi-leader replication in distributed databases.
Right. And our mission today is really to unpack all that complexity. How do you keep things consistent when, multiple people are writing data basically the same time?
And we'll look at how techniques like vector clocks and other strategies actually help with that. Think of it as getting you ready to really talk confidently about this stuff in an interview.
Okay, so where should we start?
Well, let's hit the fundamental problem first. What happens when there's just no clear order to the writes?
Good idea. Okay, imagine the scenario, like in a Dynamo style system, a key value store spread across machines. You've got two clients, let's call them A and B, and they both try to write to the same key X across three nodes, node 1, node 2, node 3.
Right. So A writes, say, the value A, and B writes B almost simultaneously.
Exactly. But because it's distributed, things don't happen everywhere instantly or in the same order.
So what kind of mess does that create?
Well, maybe node 1 gets the write from A, but it misses B's write entirely. Maybe a network glitch.
Okay.
Node 2 might get both, maybe A first, then B.
And node 3?
Node 3 could get them in the reverse order, B first, then A.
So let's pause there. What's the actual data state across the nodes then? It's inconsistent, right?
Totally inconsistent. Node 1 has A, node 2 has B, because that was the last one it saw.
Okay.
And node 3 actually ends up with A, because A's write was the last one it processed.
Wow. So then if someone tries to read that key X...
That's where the problems really show up.
Yeah.
If client B, say, does a read, it might hit node 1 and get A.
Or node 2 and get B.
Or node 3 and get A again. There's no single right answer across the system.
So the takeaway is without coordination, concurrent writes just lead straight to inconsistency. No way around it.
Because there's no single agreed-upon order of events.
Right. Now, one way systems try to deal with this is something called last write wins, or LWW. Cassandra uses this, for instance.
Ah, yes, LWW. How does that work exactly?
It's a strategy for eventual convergence. Basically, making sure all the copies eventually agree on some value.
Okay.
Each replica just keeps the value that has the latest timestamp. If two writes come in for the same key, it looks at the timestamps.
And the one with the later timestamp wins, the other gets tossed out.
Exactly. It forces an order, even if the writes were actually concurrent and independent.
That sounds simple, but forcing an order, what's the downside?
The big one is data loss. Silent data loss.
Because if two clients write concurrently and both get a success message back.
Right, but only the one whose write happened to get the slightly later timestamp actually sticks. The other write, it's just gone, vanished.
Ouch. So you could have multiple successful writes acknowledged and everything, but data just disappears.
Precisely. And it can even happen with writes that weren't truly concurrent if the clocks on the nodes aren't perfectly synced. A later write might look like it happened earlier.
That seems risky for a lot of applications.
It is. LWW is often considered safe only when you're writing to a key maybe once and then treating it as immutable.
Like using UUIDs as keys, maybe?
Yeah.
As recommended sometimes for Cassandra.
Exactly. That way you avoid these update conflicts on the same key. So, LWW offers simplicity, but at a potentially high cost.
Okay, so to really get this, we need to be clear on what concurrent actually means in this context. It's not just about timing, is it?
No, not just timing. It's about the happens before relationship, or the lack of one.
Happens before. Explain that a bit more.
Sure. Two operations are concurrent if neither one knows about the other. They happen independently, like our client A and client B writing to X without coordinating.
Okay, so that's concurrent. What's the opposite then? When one does happen before the other?
That's when there's a causal dependency. The later operation knows about or depends on or somehow builds upon the earlier one.
Gotcha. Can you give an example?
Yeah. Think about client A inserting a value, like initializing a counter to 0. Then client B reads that 0 and increments it to 1.
So D's increment depends on A's insert having happened first. B's operation happens after A's.
Exactly. There's a clear causal link. The second operation wouldn't make sense without the first one.
So concurrency isn't about nanoseconds. It's about whether one operation is aware of the other. Awareness and dependency.
That's the core idea. Dependency defines the order. No dependency often means concurrency. Understanding this is, well, it's vital for figuring out how to handle these situations.
Okay, so if we have these causal dependencies, how do distributed systems actually keep track of them, especially with lots of clients writing?
Right, that's where things like version vectors come in. There are mechanisms specifically designed to capture these causal links.
Version vectors. Okay. How do they work? Maybe we can use that shopping cart example.
Yeah, perfect. So imagine client 1 adds, say, milk to an empty cart. The database processes this write and gives back a version number. Let's keep it simple for now, say just version 1.
Okay, cart has milk, version 1.
Now, totally independently, client 2 adds eggs to their view of the empty cart. The database processes that, also gives back version 1, let's say, specific to client 2's interaction perhaps, or maybe the system handles it differently. Let's refine this.
Okay, maybe think about it from the server's perspective, managing one cart state.
Right, let's reset. Server has an empty cart, version 0, client 1 adds milk, sends write add milk based on version 0. Server processes, state is now milk, version is now, say, v1. Server sends v1 back to client 1.
Got it.
Meanwhile, client 2 also starts from version 0, empty cart, adds eggs, sends write add eggs based on version 0.
So the server gets this second write, also based on version 0. What does it do? It already processed the milk write.
Good question. It sees this new write is based on version 0, but its current version is v1. This tells the server the writes are concurrent. They both started from the same state without knowing about each other.
So it can't just overwrite milk with eggs, or vice versa.
Exactly. It needs to preserve both somehow. It might store the state as perhaps having both milk and eggs as concurrent values, maybe marking them as siblings. It might generate a new version reflecting this merged, conflicted state. Let's call it V2, which represents the merge of the two concurrent histories.
Okay, siblings. So the database knows these values resulted from concurrent writes.
Yes. Now, let's say client 1, who got back version V1 after adding milk, now wants to add flour. Their client sends add flour based on version V1.
But the server's now version V2, with both milk and eggs.
Right. The server sees the write is based on V1. It knows V1 is an ancestor of its current state V2 because V1 led to V2. So this isn't concurrent with the entire state V2. It's just building on the milk part of the history. The server can merge flour in. Perhaps the state becomes milk, eggs, flour, and the version updates to V3.
I think I'm following. The version number tells the server the context of the write.
Precisely. It understands if a write is a direct successor or if it branched off concurrently. This avoids the lost update problem you get with LWW because the server recognizes concurrency instead of just blindly overwriting.
But you mentioned siblings. Does the client ever have to deal with those?
Sometimes, yes. If the server can't automatically merge concurrent changes, like editing text, it might send both sibling versions back to the client on the next read, saying, hey, these things were changed concurrently, you need to resolve this.
Okay, that makes sense. More complex, but you don't lose data.
Right, and you can visualize this whole thing as a graph, a causal dependency graph, showing which operation happened before which, and where the concurrent branches occurred.
Like in the shopping cart, client 1 adding milk, then flour is one path. Client 2 adding eggs, then maybe ham is another path.
Exactly. And maybe client 2's ham addition happens after they somehow learn about client 1's milk, creating a cross-dependency. The versions track all this.
Okay, now, you said a single version number might be too simple, especially with multiple replicas accepting writes.
Yes, exactly. If you have multiple database replicas like node 1, node 2, node 3 again, and any of them can accept or write directly,
then they're all processing writes concurrently, potentially updating their own state independently.
Precisely. A single counter just won't cut it. You can't capture the state across all these independent nodes with one number.
So this is where the vector part of version vectors comes in.
This is it. Instead of one version number, you use a vector, a collection of numbers, one number for each replica in the system.
Okay, so if we have 3 replicas, A, B, and C, the vector has 3 components.
Yep, like A binary 0, B 0, C point 0 initially. When a write happens at replica A, it increments its counter. So the vector becomes A.1, B0, C.00.
And it stores the data associated with that vector.
Yes. And importantly, it also tracks the vector versions it's seen from other replicas during replication or communication. So A knows it's at version 1, and it knows the last it heard from B was version 0, and from C was version 0.
So when a client reads,
the replica returns the value and its current version vector. Say node A gives back the value in the vector A.1, B0, C.0.
And then when the client writes back an update,
It sends the update along with the vector it received, A.1, B0, C.0. Let's say this write goes to replica B this time.
What does B do with that vector?
B looks at the incoming vector A.1, B0, C.0, and compares it to its own vector, maybe A.0 would be 1, C.0 if B had processed an independent write earlier. It uses this comparison to figure out, is this new write overwriting a state I already know about, or is it concurrent? It then performs the write, increments its counter in the vector, and merges the vector knowledge. Maybe the new vector at B because A.1, B.2, C.0.
Oh, okay. That lets it track causality across replicas.
Exactly. It knows which updates have definitely happened before others, and which are potentially concurrent just by comparing the vectors. There are even variations like dotted version vectors, which React 2.0 used as a more efficient way to track this.
And React calls this causal context, right? Sent to clients and back again.
Right. It's the same core idea. Capture the causal history to differentiate overwrites from concurrent edits. But even with vectors, you might still end up with siblings that the application level needs to merge.
So version vectors solve a lot, but don't eliminate all complexity, especially for the application developer needing to handle merges.
That's a good summary. They shift the problem from silent data loss to explicit conflict detection and potential application level resolution.
Okay. Now, what about that other scenario? Multi-leader replication. You mentioned specific ordering issues there.
Yes, multi-leader adds another wrinkle. Let's say you have leader 1, leader 2, and leader 3. All can accept writes. Client A inserts a new record, key X, value 1, sends it to leader 1. Leader 1 says OK and starts replicating that insert to leader 2 and 3.
Got it.
Now, almost immediately, client B sends an update for key X, say, increment the value by 1 to leader 3.
Okay, leader 3 gets the update.
Leader 3 processes it, maybe the value becomes 2. It says OK to client B and starts replicating this update to value 2 to leader 1 and leader 2.
I think I see where this is going. The replication messages are racing across the network.
Exactly. Think about leader 2. Because of network latency, the replication message for the update, value 2 from leader 3, might arrive before the replication message for the original insert, value 1 from leader 1.
So leader 2 gets told update X to 2, but it hasn't even seen the insert for X yet.
Precisely. It gets an update for a record it doesn't know exists. That's a logical inconsistency caused purely by the network and replication lag. The update causally depends on the insert, but the messages arrive out of order.
Yikes. So that ordering issue is a real headache in multi-leader setups.
It absolutely is. You need mechanisms to ensure causally dependent writes are processed in the correct order, even if they arrive out of sequence. Or you live with potential temporary inconsistencies.
Okay, so tying this all back. Concurrent writes, LWW happens before, version vectors, multi-leader issues. How does understanding all this help someone sitting in a system design interview?
It's fundamental. If you're asked to design anything involving distributed storage, which is, almost anything scalable,
Right.
you will encounter these problems. Interviewers want to know if you understand the trade-offs. Why might you choose a system like Cassandra that uses LWW?
Maybe for simplicity, high availability. If occasional data loss on conflict is acceptable for that use case.
Exactly. Or why might you choose something like React that supported version vectors?
If preserving all concurrent writes and detecting conflicts is more important, even if it means more complexity, maybe client-side merging.
Perfect. Being able to discuss Cassandra's LWW versus React's use of vectors or CRDTs for conflict resolution shows you understand there's no one-size-fits-all solution. You grasp the consistency versus availability trade-offs.
It demonstrates that senior-level thinking about system characteristics.
Definitely. It shows you've grappled with the hard parts of distributed systems.
Okay, this seems like a good point to maybe run through some potential interview questions that touch on these topics.
Yeah, let's do it. Here's a classic opener. Consider a distributed key value store. 2 clients write different values to the same key concurrently. Describe the potential consistency issues.
Okay, and building on that.
So what mechanisms could you use to handle these concurrent writes? What are the trade-offs? For instance, how does last write wins work? And what are its limitations?
That covers the basics. How about one focused on version vectors?
Good one. Imagine you're designing a collaborative editing application, like Google Docs. Multiple users edit simultaneously. Okay, this gets really interesting. How would you ensure concurrent edits are handled correctly? No changes lost. Explain the role of version vectors here. How do they capture causality?
And maybe a follow-up to make it concrete.
Yeah. Can you give an example? Let's say you have 2 replicas. A and B both start at version 0. Replica A does one write. Replica B does 2 independent writes. What might the version vectors look like?
Okay, so if A writes first, its vector becomes A1, B0.
Right.
Then B does 2 independent writes. So after B's first write, its vector would be A0, B1, assuming it hadn't seen A's write yet. But if it had seen A's write via replication before its second write.
Let's simplify slightly for the example. Say A writes its vector is A.1, B0. B writes independently twice, perhaps seeing A's write in between. After B's first write, maybe its vector is A.1, B1. After its second, it's A.1, B.2, that verbalization.
A1, B2. Yeah, that makes it clear how each replica tracks its own progress while incorporating others.
Exactly. Shows the combined history. Okay, one more question focusing on multi-leader. In a multi-leader replication setup, why might writes arrive in different orders at different replicas? So what does this all mean? What are the consequences of these out-of-order writes, and what strategies could mitigate them?
These questions really cut to the heart of it, don't they?
They do. Nailing these shows you really understand distributed consistency challenges. It's definitely key for those senior roles.
Okay, so let's quickly recap. We've journeyed through the inherent problems of concurrent writes, the lack of a single timeline causing inconsistencies.
We looked at eventual consistency and the somewhat blunt instrument of last write wins, trading data integrity for simplicity sometimes.
Then we dug into the happens before relationship, the key idea of causality.
And how version vectors, used in systems like React, provide a way to track that causality, detect concurrency, and avoid lost updates, though they bring their own complexity.
Right, including potential client-side merging. And finally, we touched on those tricky write ordering problems specific to multi-leader replication.
And understanding these concepts, the trade-offs, the solutions like LWW or version vectors, it's just essential knowledge for distributed systems work.
And, as we stressed, crucial for acing those system design interviews.
Absolutely.
So to leave you with something to chew on, considering all these trade-offs, consistency, availability, complexity, conflict resolution, where might strong consistency be absolutely non-negotiable, even if it costs you latency or availability?
And conversely, when is eventual consistency, maybe with LWW or client-side merging via version vectors, actually the more pragmatic, the better choice for the application?
Think about real-world systems you use. Where do these different models fit? Thanks for joining us for this deep dive.